Hi, everybody. My name is Stefan Novak, and I'm a FreeFlyer developer. I'm excited to walk you through some ideas about how to build a cloud-based constellation ground system platform. So first off, thank you so much for really taking the time this week to tune into these presentations. The team's been really excited to have you be a part of our first users conference. And the team has really enjoyed receiving a lot of great feedback from you. So thanks for being a part of this exciting conference. So today we're going to be talking about a cloud architecture for constellation operations. Of course, no presentation at FreeFlyer Users Conference would be complete without let's see here, FreeFlyer. So we're going to be walking you through kind of building out this cloud-based architecture where FreeFlyer does a lot of the flight dynamics processing. So in the previous talk, Michael Volley performed this really interesting forensic analysis of basically trying to kind of reverse engineer sort of the operational strategy for the Starlink constellation for being able to basically establish this constellation. There's a lot that we learned from it. And what I'd like to do for this next presentation is to think a little bit about kind of how to, how do you build sort of the operational concept for maintaining such a large constellation? So there's a variety of different types of workflows that go into maintaining a large constellation, and specifically within the ground system. One of the common workflows is called Intraconstellation conjunction assessment. And as Michael talked about, in these large constellations, you have a large number of satellites that are in one single plane, and you have a collection of other satellites in another plane. And at these plane crossings, we have to basically perform this conjunction analysis to basically determine if there's going to be any close approaches. One of the questions that came up at the end of Michael's talk was about, what about doing sort of like a more of a full catalog conjunction assessment? And basically, this is a type of analysis where, for your thousands of satellites in this large constellation, are there going to be any close approaches with any other satellites in orbit? Maneuver planning is obviously pretty key to being able to maintain kind of a high quality constellation. So, maneuvers are often performed, say, on like a weekly cadence to maintain a high quality constellation. And when you perform maneuvers, maneuvers can be off nominal. And so it's critical to be able to basically measure and reconstruct what occurred during the maneuver so that you can calibrate thrusters moving forward. Next is contact analysis. So this is basically being able to determine when each satellite is going to have line of sight with, say, a ground station on the surface of the Earth to be able to downlink data. And lastly is lifetime analysis. And this is basically just kind of keeping track of how much fuel you're spending to be able to maintain the constellation and kind of keep track of, how long you're going to be able to maintain the constellation for the length of the mission duration. As we move forward with this presentation, we're really just going to be kind of focusing on just the intra-constellation conjunction assessment. So we're going to be kind of diving in and talking a little bit more about kind of what's involved for that type of workflow. Great. So we're going to start kind of diving in and kind of talking about the intra-constellation conjunction assessment. And what we're going to do is we're going to think of it in terms of like a pipeline. And a pipeline is kind of like a series of tasks that you must perform to be able to kind of conduct a certain type of workflow. And what we've illustrated here is kind of a simple pipeline that captures kind of the different stages of this conjunction assessment pipeline. So you can see in the lower left corner, there's a legend, whereas the white boxes are going to be kind of file-based inputs and outputs. And the blue boxes are FreeFlyer mission plans. So just walking through quickly, we can see that the first stage of the pipeline is to perform orbit determination. And this basically takes measurements as an input, processes them to figure out what the initial states of each of the satellites are. Moving into the second stage for ephemeris generation and maneuver planning, we take the initial states and we basically propagate them forward in time to generate ephemerides that also incorporate any maneuver planning that needs to occur. Moving forward, we have close approach analysis. So we take those ephemerides and we process them, and we look for any close approaches. And lastly, is a post-processing step where we want to take these close approach results, and we want to be able to post-process them so that we can make a report and visualize the outcomes. So we're going to be talking about this pipeline in terms of how we're going to be able to adapt it for kind of a cloud-based architecture. But it's really key to kind of, at this point, to think a little bit about what are the challenges that go into designing a ground system for these large-scale constellations. First is kind of the nature of compute. So simulating large constellations can require significant processing power and memory. And a lot of us are kind of used to, single spacecraft missions, but when we get into the scale of thousands of satellites, there's just lots of propagation that needs to occur. There's lots of, geometric analyses that need to occur. Anytime we do any pairwise combinations across 1,500 satellites, things blow up. So there's a very sort of a high demand, strong requirement for being able to have computing resources. Next is that the mission complexity can actually grow over the course of the mission design phase. And the idea here is that you're bound to have to do more processing as you're adding more analyses and you're understanding the problem as things move forward. So really, you can't plan for a fixed amount of computational resources for a large project like this. You're going to have to assume that there's going to be, a greater demand for computational resources as you go through, as you get into operations. And by the time you get into operations, you don't want to have any computational bottlenecks that end up being operational bottlenecks. And so you want to make sure that you can scale appropriately so that it doesn't affect your operational environment. Another challenge is automation. So manual QA can be very expensive for spacecraft missions. A lot of us who have worked on single spacecraft missions, we know how much time we can take to kind of go through and perform a QA for a maneuver for one spacecraft mission. But when you start talking about thousands of satellites, even if you were able to get the maneuver QA down to 5 minutes for a human to be able to look through some results to make sure that things look good. If you have 1,500 maneuvers that you're performing on a weekly cadence, and you're spending 5 minutes on each, that ends up being 125 hours of staff hours each week that go into just QAing. So that's like 3 FTEs. So we need to be able to incorporate automation to be able to perform a lot of these data processing and validation steps. Once again, as the mission complexity increases over time, as you're designing a mission and you're figuring out what are the key problems that need to solve, automation can help you move quicker. So even in the design phase, moving into operations, being able to have that automation to help you through that last stretch of the design phase can help you move quicker. And it's key to be able to plan for automation early within your architecture. Don't wait until the last minute to be able to kind of figure out how you're going to automate a lot of these pipelines. You want to make sure that you incorporate that into your strategy early on, into your architecture, so that you can benefit from it and you can smooth out any issues that come up that come along. And the last set of challenges is really just around the tooling. And so mission operators need to have the tools available to be able to monitor the constellation and address any issues. So I think today, these days, a lot of operational environments have embraced using web applications kind of as a secure and flexible way for developing tooling on top of, mission operations. And so these sets of tools will need to kind of integrate with these pipelines and help monitor automations. So these are kind of the 3 key challenges that we're going to kind of be coming back to throughout the presentation, is kind of computational resources, automation, and tooling. So at this point, I want to kind of take a step back and think a little bit about, what other domains have solved problems at this scale. Because like we're at a key point within our industry where so many spacecraft missions have been able to just kind of rely on a fixed number of resources. Because if you're designing a mission for one spacecraft, it's a lot easier to predict what's going to be needed to be able to solve that problem. But we're at a key point now where we're basically scaling out to thousands of satellites in these large constellations. And it's just an explosion of complexity and computational resources that need to be incorporated to be able to have a successful mission. When you look across other domains, you'll find that other groups and other scientists have gone through a similar type of transformation where they've moved towards cloud processing to be able to leverage this extra ability to scale to be able to tackle a new class of problems. Computational biologists, for example. Computational biologists process a lot of genomic data. And so what they're doing is that they're taking like raw human genomic data, they're processing it, and they're looking for clues that can help them be able to identify any potential new treatments for diseases. A lot of the tools that they use require kind of complex workflow management. And so they've been able to incorporate a sense of automation into their tooling as well. And lastly, cancer research institutes and organizations have actually created cancer research clouds. And the idea here is that they've built a lot of tooling that enables other researchers to be able to access their data and run their pipelines on their data. And that way they can incorporate more collaboration throughout the computational biology and life sciences domain. Data scientists are kind of another group of scientists who have been able to kind of transition to the cloud. There's a variety of different types of data scientists, right? Whether you're working on computer vision models for self-driving cars, or doing fraud detection for a payments company, or making product recommendations. The idea here is that a lot of these data scientists kind of work with this very similar set of workflows where they're needing to build out these machine learning models by training on a set of data that's always growing and always changing. And so these data scientists need to continuously retrain and redeploy these models. And they've been able to kind of transition to using cloud infrastructure to be able to help coordinate with a lot of that. And the other thing is, like, as business requirements change for a lot of these companies, like the infrastructure needs to keep up. And so being able to leverage cloud computing resources allow those businesses to be able to move fast and to grow and keep up with the demand. Okay, and then the next and last sort of domain is this, web application developers who work on like large websites. a lot of large websites, right? Whether you're talking about, Facebook, Google, LinkedIn, Airbnb, they process a lot of web traffic, and that's a lot of computation that occurs. And so a lot of these companies will leverage the cloud for being able to scale out a lot of this extra processing. Especially large websites that are kind of media rich, right? Whether they're serving lots of videos or images, there's lots of data processing that has to occur in the background, and that's where the cloud has really kind of helped meet and keep up with their demand. It's worth it to point out that for a lot of these web application development teams, there are teams called DevOps teams that even build tooling for the software developers to be able to build, test, and deploy their different services. The idea here is that there's a lot of tooling that's available to software developers for being able to interact with resources in the cloud. So as we kind of move forward, and like if this is a problem that you're kind of interested in, like think about your colleagues who work in other areas in these domains, and definitely reach out to them. Because there's a lot that we can learn from those who have gone through a similar type of transformation where they've taken these existing workflows and they've thought about how do we move it to the cloud. So at this point, we're going to be talking a little bit about what the cloud is, and I kind of want to focus more about kind of what do I mean when I talk about the cloud for this presentation. And there's kind of three key points that I want to point out. First is the cloud provides sort of on-demand computing resources. And this is going to be definitely very useful for us to be able to scale out analyses on demand so that we can take advantage of automation to be able to process a lot of these complex workflows. Different cloud providers provide a collection of additional services to facilitate automation. So we'll see that the cloud is more than just hosting virtual machines somewhere where you can connect in. A lot of cloud providers have actually built additional services that can actually help us with the type of automation that we're seeking. And lastly, the cloud is a platform for building tools to help with data processing. So what that means is that we'll see that you can build additional sort of web application services that can be built on top of these automations and these pipelines. So the idea is that we would be able to kind of also leverage the cloud to be able to provide the tooling that's required for operators to maintain Constellation. Okay. So I'd like to kind of dive into one specific cloud provider that I've been working with recently. There's a variety of different commercial cloud providers, right? Whether it's Google Cloud, Microsoft Azure, and each of these different cloud providers provide some similar services. So I definitely encourage you to kind of take a look at what other commercial providers have, but we're going to be kind of talking about Amazon Web Services for the scope of this presentation. So there's 4 key services that I would like to kind of just quickly walk through and kind of share with you, because these are going to be the cornerstones for this architecture that we're going to be walking through shortly. So the first is Elastic Cloud Compute. And basically the idea behind EC2 is to just be able to rent a virtual machine in the cloud. I mean, the idea here is that you can spin up these virtual machines on demand, and you get charged just by the minute. So if you can efficiently manage these compute resources, you can have, very efficient cost model where you're not having to use a lot of computational resources throughout a whole year, and it costs a lot to do that. You can just spin up the resources you need kind of on demand. One of the capabilities of EC2 is to be able to pre-install software on these virtual machines to take a snapshot to create an image. And at that point, you can use that image to then create new instances. So the idea is you can pre-configure them, and it gives you a little bit of extra flexibility. And the other main point is that EC2 provides a lot of options for high-performance virtual machines. And they've done this to really kind of cater towards scientific programming workflows and machine learning. So whether you need a lot of processing power, memory, or even GPUs, EC2 has a lot of options to be able to help us with the type of processing that we're needing to do when it comes to flight dynamics simulation. The next service is Elastic Container Service. And this is kind of, a sort of an emerging technology in the last 5 years. Containers are kind of like lightweight virtual machines that don't have as much overhead. And the idea is that AWS, through the Elastic Container Service, can run containers on EC2 instances with ease. And what that means is that this service kind of abstracts away the code that you want to run from where it actually gets run. So we'll see that using ECS allows us to be able to run different parts of our pipeline in the cloud without having to specifically designate which server it's going to run on. Okay. Next is a service called Batch. And Batch is a service that allows running a series of containers as a series of jobs. And so the idea here is that, a lot of the different types of workflow management tools that computational biologists and data scientists use require kind of sequential processing of data. And Batch helps coordinate and orchestrate the execution of each of those different steps. Batch provides job dependencies. So if halfway through your workflow a job fails, then it knows not to run the remaining stages of the workflow. And there's also a notion of array jobs, which allow you to be able to spin up multiple instances of one specific stage so that you can actually incorporate parallel processing within your workflow. Batch also provides sort of automatic logging facilities, so it's really easy to be able to drill in and kind of view the standard output from your executables. And Batch also provides resource management. What that means is that when you kick off a pipeline, Batch will go out and actually allocate EC2 instances, create a cluster for your Docker containers, and then perform the execution on that. When your job finishes and you're not using any of those computational resources, Batch will go ahead and return them back to the pool. So Batch kind of facilitates that sort of dynamic resource allocation for us without us having to worry about specifically spinning up different virtual machines in the cloud. All right, and the last service is the simple storage service, S3. This is a cloud file storage solution. The idea here is it kind of provides this file storage without having to worry about disk space. There's a simple API that allows us to copy files kind of in and out of cloud storage. And this mechanism works really well when it comes to storing intermediate data because we get really good performance and cost characteristics when we're just kind of copying data around within a data center and not necessarily having to download it ourselves. So when we run through our pipelines and each of these different stages is generating lots and lots of data, being able to store data within the data center, within the cloud, ends up being a very, very good solution. So these 4 different services are going to be kind of the building blocks for the architecture that we're going to be building very shortly. So let's talk about adapting our intra-constellation conjunction assessment pipeline for the cloud. So this is the pipeline that we just kind of talked about before, where we have orbit determination, ephemeris generation, close approach analysis, and post-processing. We're going to transform this to be able to deploy on top of these different services that we just talked about. So the first thing we're going to do is we're going to split up each of these different stages into separate Docker containers. And so you can see here a Docker container includes the FreeFlyer mission plan that executes and the data that's generated. You'll see that we kind of broke up the arrows where we're not necessarily passing data across the Docker containers yet, but we're going to be able to rebuild on that shortly. So the next step is to be able to take these Docker containers and wrap them within a batch job. So this allows us to run these containers in sequential order. If one job fails, then the other jobs won't run. We get logging, we get resource management. The next step is to start bringing in cloud file storage. So as I mentioned, that we're going to be using S3 for being able to store intermediate data files. So since the pipeline starts with inputs, the measurements that feed into the orbit determination mission plan, we're going to start with the measurements data in the cloud and cloud storage. So the first step in terms of running the orbit determination job is to be able to use a pre-processing step to copy the measurements data from cloud storage into the Docker container so that the orbit determination mission plan can go ahead and process those measurements data and generate the initial states. When that mission plan is completed running, there's a post-processing step that will take that data within that container and basically copies it into cloud storage. When the Docker container completes running, all the local data that's generated is kind of just deleted, and that Docker container is destroyed. So it's really important to be able to copy the data that you need out into sort of this intermediate storage through S3. So the next step is to be able to now run the next job, which is the ephemeris generation and maneuver planning. And so our pipeline will use an additional pre-processing script to be able to copy the initial states from cloud storage into the Docker container where the ephemeris generation mission plan can run to generate the ephemerides. Similarly, there's a post-processing step to be able to copy out those ephemerides into cloud storage. And we continue on and on. So we have a pattern here where we've taken our FreeFlyer mission plans. We were going to run them inside of Docker containers as part of a series of batch jobs. And we use these pre-processing and post-processing steps to be able to move data in and out of cloud storage. So at this point, I want to kind of shift gears and actually walk through like a demo to now walk through executing this pipeline and actually seeing how does this automation work. So keep in mind that this is kind of what the operator's workflow should be, is that they should either push a button or there should be some automation that kicks off the pipeline. The operator can go get a cup of coffee, and by the time they get back to their desk, they can view their results. But we're going to be walking through and poking around through AWS to kind of see what's going on. But keep in mind, you don't need to have to do this as part of your workflow. We're just going to kind of poke around and kind of see what's happening in the cloud. Okay, so let's say we've pushed the button, we've kicked off the pipeline. The first place we're going to go to is we're going to look at AWS batch. So this is where the jobs are going to be running. And so the first thing you kind of see at the top of the screen is sort of an overview. And this kind of shows you how many jobs are running and how many jobs have succeeded and failed. When we look elsewhere on the page, we kind of see that we have a series of job queues. And for this demo, what I've found to be really useful is to be able to have separate environments for the pipeline, because it's important to be able to have a separate environment for development purposes, one for test, and one for production. And you'll kind of see this pattern kind of sprinkled throughout the demo, is that there are clear distinctions between different environments. And so if we take a closer look, we see that there's 4 pending jobs for the test pipeline. So we're going to be using the test pipeline throughout this demo. So at this point, we submitted the job. The jobs are pending because AWS needs to kind of spin up the resources. So let's go ahead and let's click on the 4 pending jobs and drill in. So we see the 4 different stages of our pipeline. And it's actually kind of in descending order. On the bottom, the orbit determination is the first stage, ephemeris generation is the second stage, close approach analysis is the third stage, post-processing is the 4th stage. You can kind of see how each job has a different set of configurations. As I mentioned earlier, AWS Batch provides different types of job types. In this case here, we're going to be leveraging array jobs to be able to run multiple instances of a job to be able to perform parallel processing on separate planes. And lastly, you can see that once again, these jobs are pending, which basically means they're waiting for resources to be available before they can start running. On the left side, there's a link for compute resources. Let's kind of dive in there and kind of see what's going on. So AWS Batch has this notion of compute environments, and these are basically the cluster of EC2 instances that will be able to run our Docker containers. So when we kind of take a look here, we see that there's a compute environment for each of the different environments that we're working with. Let's go ahead and drill into the compute environment for the test environment. Okay, here's a details page, and basically the details page for the compute environment gives us a link to the actual EC2 cluster. So let's go ahead and click on that and kind of drill in. So now we're at the ECS layer of kind of the technology stack, and we can see that there's several clusters that correspond to different environments. These are all auto-generated, but we can see there's one for the test environment. Let's go ahead and check that out. And so here's our cluster. When we take a look, there's kind of some status information that tells us like what resources are available. There's nothing here quite yet. But if we kind of take a look at this ECS instances tab and we kind of drill in, we see there's like a little hint here to say that you can access EC2 to be able to add additional instances. The batch takes care of this for us. All this resource management is kind of occurring in the background. So when we switch over to EC2, right, which is the lowest sort of level of the virtual machines that then the ECS is built on top of, and then batches on top of that, we actually see that there's two virtual machines now that are being initialized. And these two instances are going to be part of the cluster that will execute the Docker containers. So what we're going to do is we're going to kind of take a step back. We're going to go back to ECS. And we've noticed that like the two EC2 instances are now part of the cluster. And stepping back to the batch page, we can kind of still see our jobs are still pending. But when we start to kind of drill in back down into the orbit determination stage, we'll find out that eventually our jobs will start running. And as I mentioned, for the orbit determination stage, we're running an array job. In this case here, this is a fictitious satellite constellation with 6 planes. We're running one instance of each mission plan for orbit determination for each plane of satellites. So we're able to run 6 instances at once. Okay, so there's a little refresh button on the right side. We're going to go ahead and push that. And we've seen that just within that time, 2 jobs completed running. So when we refresh again, we'll kind of see that all of the jobs have finished running. Cool. So on the left side, we're going to go back to the dashboard. There's a little link there. And we see now that one of our jobs succeeded running. So 1 down and 3 to go. So let's just take a look at the pending jobs. We have the 3 jobs left. We see that the orbit determination job isn't there anymore, but let's go ahead and drill into the EFEM generation. And once again, we see that these jobs are already running on top of the little cluster that we've set up. So when we go ahead and refresh, we can see that the status updated, and we can kind of sit here and wait for these jobs to kind of finish running. Keep in mind, we're not necessarily doing any orchestration. We're just clicking around and seeing all of this automation occurring that's running through our pipeline. Okay, so within a minute or so, all of these mission plans finished running. So let's go back to the dashboard and see what's going on. So now we've seen that there are 2 stages that finished running, right? So while this pipeline continues to run through the last 2 stages, let's jump over to S3, to cloud storage, to see what's going on over there. So the first thing you'll see in cloud storage is a number of what are called buckets, which are kind of like top-level folders for storing data. You'll see that we have a bucket for each one of the environments that our pipeline is running in, right? Development, test, production. Let's go ahead and take a look at the test bucket. The first thing you'll notice is that just the way that this was kind of organized is that within the cloud storage, there's a time-stamped folder for the specific job that was run. So this allows us to kind of have multiple runs, and we can kind of organize data appropriately. So let's go ahead and take a look at that. And what we'll see is we have 2 folders for each of the 2 stages so far, orbit determination and EFEM generation. Let's go ahead and take a look at orbit determination. So what we'll see here is that these are the initial states that were generated from the first stage of the analysis for the orbit determination. And this basically is the intermediate storage that we've been talking about. You can access this data here, you can download it, you can access this data programmatically. But this is just kind of showing that this is where that data is being stored. So let's jump over to the other folder for the ephemeris generation, and we'll kind of see the same thing. We have a collection of ephemerides that are in this folder. So let's go take a look at batch and kind of see what's going on with our pipeline. And in the jobs listing, we see that we're down to these 2 last jobs. Let's go take a look at the close approach stage to see what's going on. We can check in on the status. We can see that once again, we're running multiple jobs at once for each plane, and 2 of the jobs have already finished running. So we can go ahead and just kind of click through and watch these statuses change. Okay, at this point, all the jobs finished. So let's jump back to the dashboard. And now we see that 3 of the stages are finished running. And so let's just go ahead and refresh, and we find that all the jobs ran. So when we jump over to S3, we find that we have these 2 additional folders for the other stages. In the close approach analysis folder, we see that there's different files for containing conjunction data. And if we jump back to the folder, we take a look at the post-processing folder. We'll find that we have one image in this folder, which is a plot containing the results. So we can kind of drill into that. There's a URL for this file that we can access. And basically, we can get the final results for this plot. And what this shows, once again, this is a fictitious sort of constellation that we've constructed. We see these 2 bands, 2 blue bands, and these are basically the close approaches from 2 planes that have their close approaches near the equator. And these are basically 2 planes that, their right ascension of the ascending node is separated by 180 degrees. So they're basically crossing on opposite sides of the Earth. And so one band is kind of on one side, the other band is on the other side of the Earth. Okay, so keep in mind that this entire process is automated, because we kind of said, like, you push the button, this pipeline runs, and you can step away. All of this is being orchestrated. Compute resources are being spun up for you. Your pipeline is being run in parallel for certain stages. All of this is automated. And the key point here is that keep in mind that FreeFlyer is being executed in the cloud for each of these individual analyses. Okay, so moving forward, there's a few ways to kind of think about extending this architecture. So we have this pipeline that we can execute. There's a variety of different circumstances where you want to be able to execute the pipeline. So I call them trigger events. So you might want to start the pipeline based on the availability of data. So as we said, measurement data might come in, and just the existence of that measurement data, you can set up a trigger to automatically run the pipeline based on that. You might want to schedule the pipeline to run at certain intervals. You might want to use event notifications. A lot of cloud providers provide eventing systems. So just based on an event that pops up somewhere in the system, you can kick off the pipeline. And lastly, you can build web applications and have a web interface where the operator can push a button to be able to kick off the pipeline. And then on the right side, we have different actions that can occur when the pipeline finishes running. So we saw like that one little plot, but there might be different types of data that your pipeline is generating. So there's a variety of different actions you can take. You might want to send results to an operator over Slack or email. You might want to do some additional processing of data. That additional processing could be conditional on the results from the pipeline. So if some key metric passed a threshold, you might want to perform some additional automated processing on that, but otherwise, just log it and don't notify anyone. And lastly, you can take the results and you can push it to another service. You might want to take these results and push it back to the web application so that the operator can see the results. Another important area is networking and security. I won't spend too much time on this, but I kind of just want to walk you through kind of how to interpret this diagram. In the top right corner, you kind of see the S3 bucket and AWS batch that was used to kind of execute the pipeline. Kind of moving towards the lower left corner, you'll see that there's different areas that correspond to different subnets and security groups for this cloud-based architecture. We see that AWS batch and S3 kind of integrate with the compute environment where our instances of FreeFlyer are running. But those instances of FreeFlyer running inside the compute environment need to be able to integrate with a FreeFlyer license server to be able to manage licensing. And that FreeFlyer license server needs to be accessible to a license server admin who is potentially browsing through securely kind of through an internet interface. And so this is kind of an important part of documenting these types of architectures, is the network and security aspects of it. I came across a number of helpful tools that allowed me to develop this cloud infrastructure and to be able to rapidly deploy it. The first is Terraform. Terraform is a tool that allows you to manage cloud infrastructure through file-based configurations. Basically, Terraform allows you to have one file that you can describe all the different resources that you want within the cloud. And just with one command, it can spin everything up. Terraform also performs state management, so it keeps track of what's actually running, so that if you change your configuration, Terraform knows how to apply the right set of updates. And there's support for a variety of different cloud providers. Packer is another useful tool that I came across. And Packer automates building of different types of images through file-based configurations. I found this to be really useful because you know, on the one hand, we have the Amazon EC2 machine images that are used to, you know, create the network license server. We also have the Docker images that contain FreeFlyer and the different mission plans. Packer allows us to be able to configure both types of image configurations through one single interface. It was quite convenient. And there's also support for a variety of different cloud providers as well. And lastly is a tool called Ansible. And Ansible automates installing of software and configuring systems. So Ansible integrates really well with Packer to be able to build out the AWS EC2 images along with Docker images. And once again, Ansible uses a file-based configuration as well. So the key thing about all these three tools is that they're all based on file-based configurations that you can easily version control, so that you don't have to actually manually click through any user interfaces to set everything up. You can actually have one repository that contains your full infrastructure configuration that you can rapidly deploy. So at this point, you know, we have a good understanding of how these different technologies kind of work together, where we want to be able to kind of build pipelines, tooling, and to support operations. If we take a look at this diagram, starting at the bottom and moving up, we can see at the bottom, you know, we have, you know, a solid understanding of networking and security. We can then have compute instances on top of that, the EC2 instances. We talked about how when we abstract out containers on top of the compute instances, it makes it a lot easier to be able to, you know, run our custom code regardless of where it's being executed. We then incorporate this batch processing layer, which basically allows us to have these jobs that can run in order. And then on top of that, we have pipelines, and pipelines are kind of more of a general abstraction. And then up tooling and automation, and then up to ops. It's really important to think about who is responsible for kind of building and maintaining each parts of this system. You know, obviously you have the cloud engineer who's working a lot with the cloud technologies, but you have the flight dynamics engineer who's working on the pipelines. You'll need an application engineer to build the actual applications and hook up all the automations. And then you're going to have the operator who's going to be working with those tools. The boundaries between each of those different roles is kind of fuzzy, and you know, it's really key to have good collaboration, because, you know, the cloud engineer and the flight dynamics engineer should be working together closely on the integration between pipelines and batch processing. So it's really important for them to sit next to each other and communicate often. Okay, so at this point, I kind of want to wrap things up. Just to kind of reflect a little bit about what we've shown today. We've demonstrated running FreeFlyer mission plan workflows in the cloud. We've taken this intra-constellation conjunction assessment pipeline that was a series of FreeFlyer mission plans, and we were able to adopt that to be able to adapt that to run it within the cloud. We talked a little bit about how we can learn from what other domains have done in terms of how they've been able to move to the cloud. And a lot of what I've shown you today isn't anything that's necessarily new or novel. I'm simply taking the knowledge that I've learned from working in these other domains and talking with friends and colleagues who have worked with this to figure out how we can bring these ground system platforms to the cloud. Cloud platforms are ideal for large-scale ground system architectures. In the very beginning, we talked about the 3 key challenges were compute, automation, and tooling. And these cloud platforms provide us sort of like the on-demand compute, tools and services that are built in for helping with automation, and basically the APIs and other interfaces and resources for building applications and tooling on top of those pipelines and automations. And lastly, collaboration between flight dynamics engineers and cloud engineers is key. And this is something that I've seen in other domains, like in computational biology, where we're at a point where you kind of need to be an expert between 2 things. And I've seen computational biologists take strong interest in cloud technologies, and I've seen them work with cloud engineers really, really well. And when you have good collaboration between those 2 different roles, you're actually able to build out a strong foundation for these types of platforms. So that's it for the presentation. I just want to thank you again for sitting in. We're really excited to have you be a part of this week's conference.
Stefan, really enjoyed how you put in coffee in that workflow you showed earlier, and how you showed FreeFlyer and on the cloud architecture can solve the automation, testing, tooling, and computing problems that you mentioned, and built everything up from scratch. So the first question is, is your orbit termination plan performing one satellite solution or multiple satellite estimates?
I'm sorry, can you repeat that question?
Yes. So is your OD plan performing one satellite solution, or is it multiple satellite estimates?
We're providing individual estimates for each of the satellites. So every satellite within the constellation gets its own solution.
Okay. And I believe you can configure that in the mission plan however you want, right?
Yeah.
Okay, so we have a lot of questions on licensing. Since there are a lot of instances of FreeFlyer running on the cloud, how is FreeFlyer licensing set up? And let me combine that with another question. How does it scale,
Yeah, so for this configuration, FreeFlyer has to be licensed to be able to support a maximum number of concurrent licenses that can be checked out. So based on the maximum level of concurrency or parallelism that you want, that would be determined by the number of licenses that you were able to purchase through like a network license setup. So the idea is that there's a network license server that runs in the cloud, and each of the instances within the batch environment that runs, each of those instances of FreeFlyer need to check out a license for the duration that it's executing.
Okay, and I believe if somebody needs a large number of licenses, there's the HPC licensing model that we have that we don't regularly talk about because it's it's not that common, but that's also an option if there's a use case where you need a large number of instances of FreeFlyer up and running at the same time, right?
Yeah. And if you're really interested in this, definitely talk with the sales team, because it's definitely a conversation that we can kind of talk through different options.
Okay, so how much does it cost each time you run the pipeline that you showed?
I would say it's pretty cheap. I've been kind of developing this new architecture over the last couple weeks, and I think I got billed about $15 over the course of 2 weeks. It's really depends on the types of instances that you choose. But if you're able to kind of scale out and run each of these mission plans, if they just take a few minutes, really I think it's pennies per per minute or per hour pretty much, so it's very cost effective.
Yeah.
There are Amazon Web Services EC2 calculators out there that actually kind of tell you what the hourly rate is for each of these instances.
Yeah, and thank you, Stefan. And that sounds very affordable. So you mentioned how developers should work with the Flood Dynamics team, and how that collaboration is very important. And it's you need to have, wear different hats. So how did you do it? You have a very strong background in development, right? So how can you give us, snapshot on how often you communicate, or perhaps how can you write a mission plan that would be compatible with this architecture?
Yeah, so I worked closely with Michael Volley. He was kind of like the flight dynamics engineer. I was kind of like the cloud engineer. We worked very closely to really kind of make sure that we had good inputs and outputs and configuration of the mission plan. So for example, FreeFlyer supports parsing JSON. And so if there was ever any sort of external configuration, it would be convenient for the cloud engineer to be able to pass JSON into FreeFlyer for FreeFlyer to parse out the configuration. So it's really important just to make sure that we kind of coordinated on what those little handoff points were, and especially for kind of the inputs and outputs for files. So that's something that should be pretty key to be able to figure out what are those conventions that we're going to use early on to start making it easier to be able to take the code as it's being developed to be able to deploy it into the cloud so that you can kind of start working out any kinks.
Okay, that makes sense. So diving into that a little bit, do you think a developer needs to have FreeFlyer experience to have that conversation, or is it just enough to communicate closely with somebody with the flood dynamics expert?
Yeah, ultimately their expertise should be kind of in sort of cloud infrastructure. Knowing a little bit about the types of problems that are being solved can definitely help, because the cloud engineer would be able to pick up on any anomalies or anything like that. So I would say that it's good for them to learn from the flight dynamics engineer in terms of the problems that they're trying to solve, especially the inputs and the outputs. But strictly what goes on inside the FreeFlyer mission plan, they can kind of treat it as like a little bit of a black box.
Yeah. All right. So this question is for the first point that you made. You mentioned that cancer research organizations, as an example, they have their own platforms, their own clouds to share data. Do you think the astrodynamics community could or should create a cloud platform for sharing data as well? And what kind of challenges would we face if that's what you think we should do?
Yeah, that's a very good question. So one of the reasons why the cancer research communities have done this is because there's a mutual interest for them to share data to be able to get a better understanding of genomics. As for the flight dynamics community, we kind of see a little bit of that. I mean, obviously, there are organizations that publish, TLEs to be able to share this information. So I think just maybe it doesn't translate fully just in terms of the types of data and types of problems that we're working with, but there might be an opportunity there for researchers potentially.
Yeah, I would agree with that. So today's topic is about constellations, and you showed an example of how to use a cloud architecture for a constellation. Does it make sense, or is it worth it to use similar architecture for just one or two spacecraft?
Yeah, I think so. I think the cost effectiveness of this architecture does scale down to simpler missions. Obviously, it's a lot easier when all your infrastructure is in the cloud. Everyone can just have their own laptop and access the same browser-based tools. You don't necessarily have to have any dedicated server infrastructure. So I think that although we've kind of talked about how we can really scale out for some of these larger scale problems, I think that this approach also really does scale down for simpler missions as well.
Okay. So this is the last question we have. I hope we have more time. So if anybody has more questions, please shoot. So Stefan, did you model response activities for CDM alerts? That would seem asynchronous relative to your workflow. Is that something you do?
Can you repeat the question?
Did you model response activities for CDM alerts?
Nope, I didn't. I'm not too aware of that.
So my question to you, that is something that you can probably do, right?
Yeah. It would be great to know a little bit more about kind of what that would entail. But I think the key point is that this architecture is obviously very extendable. It's very modular, so it can grow and incorporate additional requirements for modeling and other types of actions like that.